The mission script files may be the most complicated game data asset in the Traffic Department archive. They contain the information used to initialize missions and could potentially have many moving parts. We'll now build several Python utilities in order to understand how these files can contribute to our prototype. Let's copy all 59 mission files into a new workspace. We can see that these files are all the same size. That's good because fixed width archives are usually easy to take apart. Looks like I grabbed an extra file. In fact, there's another extra file up here too, an unused mission file, which I know isn't included in the actual game. Episode 3 only has 19 missions. Let's remove them. Before we look at the mission files, what could be some of the things that could define a mission? Well, maybe a map, an overall goal, ships in the mission, text data banners, special points of interest or objects. Let's take a look at the first mission file. I think we're used to no headers by now. Looks like there's some repeating blobs of data throughout the entire file. No text data or words. Actually, these files seem pretty sparse with many null bytes. Let's look in the second mission file. Well, this looks similar with repeating blobs and no text data. Now, although the blobs are significantly different, it looks like both files have the same overall type of organization, but the values could be drastically different, including different lengths. Now, it looks like there's a small blob near the beginning separated from the large area. Doesn't quite start in the same place in both files. I think we can eliminate the idea that there's useful text data in this file, but I'll be honest, there isn't much to go on. The one clue about the data I see is that the blob sections appear to change by a value of 1, and they frequently go for long periods without any change. That's interesting, but not helpful at this point. Now, I only looked at 2 files. We have 57 more we could look at, and that would take more time than I have. Fortunately, the Python interpreter can go through these files for us and find interesting information that might help out. Here's the plan. We'll set up a 2D array, which in Python means a list of lists. We'll open the first file and start reading in all 20,080 bytes. The byte positions are in the first dimension, and the second dimension is the file number. So then we'll read the second file in and lay out its 20,080 bytes, and so on until we have all 59 files in memory. This is our data array. We'll then set up another one-dimensional array to capture the maximum number of each byte across the 59 files. We could have probably used different metrics for the array, such as the cardinality or maybe even the range, but I think the maximum is probably the most useful in this case, and it's simple. Let's go get these data. To open all the files, we'll need some extra operations, so we'll import the OS and glob module. Let's initialize our 2 arrays. First, we'll load all the files by grabbing each of them by name from the current directory and opening them for binary read. For each line in the file, we'll have to read each byte. There may be only one line, so this might actually be a loop of 1. Now we have to append the byte list for the current file, and we might have to use an index. Add that index to the top. The first byte will fail because there's no sublist in the position. Alright, I'll be lazy and error trap the first byte. Let's close the file descriptor. We don't need 59 loose files floating around. Okay, this is some terrible code right here. I meant to call the index file index, not byte index. Definitely should have initialized the empty list before the byte up here rather than hack the error trap. Oh well, it should work, but minus 10 points for readability. Now we'll calculate the data max array, which just reads each of the 20,080 byte positions across the 59 files and finds the maximum value for each position. Now, technically, this is all the actual data work, but I think we need an easy way to read the output. Python is great about spewing more brackets and commas than actual useful data, which doesn't help us analyze quickly. So we'll want to be able to choose which bytes to look at, so I'll add an option for min-max window, which defaults to the whole file. We'll want to see which offset of each byte we're looking at. Then we'll loop through the whole data max array and print out bytes within the window. I'll go ahead and print the offset in hex. This should now show us the maximum value of each byte across all mission script files. We'll run this file and use the -I switch to stay in the interpreter after it finishes. But first, we'll kill this syntax error. Looks like I forgot to close the file name string. Try that again. Well, that was fast. Let's see if all the data are there. Looks good. I'm seeing expected values, decent amount of zeros in the mix too. Looks like our data max array ends at 4E6F. Let's see if that's all 20,080 bytes. Well, that address is off by 1 because we have to count the 0. Looks like it's working. Let's look at the first 32 bytes. Okay, so it seems all the bytes except for byte number 10 aren't even used. If we want to look at the value of all 59 files for, say, the first byte, we directly access the data array at offset 0. As we expect, all 59 files are showing values of 0 for the first position. The Python interpreter lets us use hex offsets too, so let's take a look at the byte that has the non-zero value. Looks like only one mission among the 59 uses this byte, hence the non-zero max. I think I'll call this an anomaly and just say there's no useful information in the first 2 paragraphs of data. Let's move to the next 32 bytes. That's 32 through 63. Alright, now we have something to talk about. Looks like the bytes between hex 28 and 3B. Let's see how many of these bytes these actually are. We'll subtract the last position with the position before the first. Looks like 20 bytes has some significance. Let's see the actual values for those 20 bytes across the 59 files. We'll loop through the hex offsets. Here's the usual Python mess. Now I see a lot of maximum values of 255 and some zeros too. Now in my experience, 0 and 255 are used as plug values for bytes and are usually ignored or unused. So if we ignore those, we see something interesting. All the other values don't go higher than 8. If we jump back to our hex file, those bytes between 28 and 3B all contain either FF or a number less than 8. Remember, one of our theories about this file is that it probably contains data about ships. Well, just how many types of ships are there in the game? We know this because we've already pulled out the graphics for the ships. Let's go check. Well, it looks like there's actually 9 ships, but we didn't count 0. So this time 0 might be significant because 0 through 8 can give each ship its own index. Looking at the file again, I'd estimate that the number 7 is the most commonly referenced number. Looking at the ships again, 7 corresponds to the basic enemy ship encountered from the very first mission and throughout the rest of the game. Well, that's enough evidence for me. These 20 bytes reference the type of ship, and I'm guessing that the value 255 represents an unused ship slot in the mission. Let's work down a bit more, say bytes 64 through 100. Well, it looks like the start of a new section here at hex offset 50. Let's restart at that point and see if we can find an end. Nope. So we saw from the first 2 mission files that the data tends to have long blocks of valid data, and both files look like the sections had differing lengths of values. Let's take an overall look at the rest of the file. There's quite a few unused spaces. I'm noticing that most, if not all, of the values are below 200, which would be consistent with the size of the map being only 201 by 201. I'm suspecting that these values are associated with the ship values at the top, but we need a better view of the structure. Let's add an analysis that could show us the position and size of the section breaks. Now by section break, I mean the locations in our maximum data array where all bytes are 0, but then the next byte is non-zero. We want to compare the lengths of the section 2 to see if there's any consistency. Back in our script, we'll add a new function that reads through the data max array and finds the breaks. Now for each member of the data array, we'll check to see if the previous member was 0 and if the current member is not. Then we'll save the position. Now compare it to the last position to determine the size of the section, -1 since we're only looking at points of rising data. We'll print that interesting find in hex with the size. When we're done with the current output, we'll save the most recent interesting byte as the last interesting byte. For the most part, this will be setting it to itself for the uninteresting cases. Let's give it a shot. So this is interesting information. We see the start of our long block of information here at hex 50. And note that the size of the block that starts there isn't discovered until it finds the next section break. So this size of 499 refers to the 499 bytes in a section starting at hex offset 50 on the previous line. But the most interesting part is that these section sizes repeat. I'm starting here at 499. We see 2003, then a long chain of 500s, and then finally a 1001. This exact pattern repeats down here. The vast majority of sections are a size of 500 bytes, but those that are not are some multiple of 500. I'm willing to bet that those sections are actually multiple 500 byte sections that our test doesn't see the break, because each byte in a section is used. The way we tested for a section break wouldn't have detected if one mission file had a full 500 byte block. Instead, it would bleed over into the next 500 byte block. I'm sure that's what happened here. Because of the symmetry between the two groups of sections, my guess is that their purpose is closely linked. I mean that the block of file size 499 starting at address 50 is highly associated with the block of size 499 down here starting at address 2760. Well, how far apart are these blocks? Exactly 10,000 bytes. Now, is it true for the last section in both groups? That's 4C8E minus 257E. It is. Now we have this top section with the ship data that goes from byte 0 to byte 50, which is 80 bytes. Well, we've accounted for every byte in the 20,080 byte file. My argument is that both 10,000 byte blocks are composed of 500 byte sections. Now how many sections is that? Well, it looks like 20. There are the same number of sections as there are ships defined at the top. Two 500 byte sections for each ship. And we made the guess earlier that the byte values are somehow associated with the map. The theory I'm going with now is that the top group are map coordinates for ships, maybe the X coordinates, and the second group are the Y coordinates, or vice versa. Now we can back this guess up by going to the hex editor for any mission file and see if the length of one section values for a single ship in a mission has a matching section in the second group with the same length. Every grid coordinate needs a match to make a pair. Since we already know the hex offset of 50 and 2760, let's check those of mission 1. The first section has a length of C6, and so does the second section. More evidence is that in the first section, for every string of bytes that's the same on one side means that the matching bytes on the other side are not the same. They're changing by a value of 1 each time. When a ship isn't moving in one coordinate direction, it's because it's currently moving in the other direction. These values are probably paths through the map that the ship is supposed to follow. Let's prove this too. We'll copy the map from the first mission to our workspace. We'll start a new Python script. First, let's get the map up showing the collision areas versus non-collision areas. We'll open the map file with one line. I bet the file descriptor just got lost in the shuffle there, but I'll let the garbage collector handle it. Set up the map data list. Let's remember to account for the column major storage of the map. So for each X position in the map, we'll have to create a sublist. This is the way it should have happened in the last script we made instead of hacking the error trap procedure. Now for each column, we'll check the value that we're reading to see if it's a solid area or an open area. Now, I don't know which is which right now, so let's go to the map file with the hex editor and find an open road area. So these bytes here should be in the middle of the road. Looks like values 31, 32, and 33 hex. Let's mark the open spaces in a file with a period, just like in a roguelike game. So everything that's not open, I'll mark with a capital letter O. Now we'll print the map, making sure it's in column major. If this doesn't work out, I'll just reverse it here at the print routine. All right, let's run this thing. Okay, my console width and font size probably needs to change to match the map. Let's take care of that. Now we'll rerun. And there's the mission map. Note that these aren't all the open areas. In fact, the roads are actually wider than they appear because other sprites along the edges of the buildings provide shadows that aren't collision areas, and I didn't check for those. I'm betting this is sufficient for our test, though. Now let's go back to the script and draw the paths from the mission file. So for all 500 bytes in a section, we'll read in both the bytes starting at offset 50 as the x-coordinate, and the y-coordinate, I forget the offset address, but I remember it's the 50 offset plus 10,000, and then the byte value. Let's say x marks the spot. Rerun the script. And there we go. We see a perfectly drawn path for a vehicle traveling through the map. Now we can't tell from here whether it's entering the map and traveling to the building or the other way around, but we can assume that the first byte is also the starting location for the ship in the mission. We now know how the mission script files work. There's an 80 byte section at the top with 20 bytes that define the ship types. The rest of the bytes are either unused or they're initialized at 0 and the memory locations are used at runtime. The remaining sections provide path waypoints for all 20 ships.